First session, I am the chair of the session. I am Anant Raj. I am an assistant professor here, very new, I think newest in this department. Uh, so in so there would be 4 talks in this session. One by Professor Palash Das from IIT Jodhpur, reimagining computing through systems that drive AI and AI that saves systems. So like very entertaining talk. I am looking forward to that. Then later, like we will have a talk from Professor Chandan Karfa from IIT Guwahati, machine learning for electric design and design automation. Then after the coffee break, we have 2 more talks. One by Professor Anupam Sanghi from IIT Hyderabad and other by Professor Arpit Agarwal from IIT Bombay. So I'm without delay, I'm just will read introduction for Professor Palash Das. So Palash Das has received his BTech degree in CSE from the West Bengal University in CSE, from the Indian Institute of Engineering Science and Technology, Sibpur. He completed his PhD from IIT Guwahati in April 2022. Presently, he is working as an assistant professor in the Department of CSE at IIT Jodhpur. His research interests include near memory processing, hardware designing, AI ML accelerators, and emerging memory technology under the broad domain of computer architectures. So I'm looking forward to your talk.
Thank you so much for the introduction. Thank you, Dr. Sumit, for inviting me here. Good morning, all. I have seen you have asked so many questions last day. So it seems you have a decent background in machine learning, AI, and all that. Yes or no? So how many of you are having background in computer architecture or doing some sort of work in systems, or you have gone through the courses of computer architecture? Better. Right. So yes. So my it's going only one direction.
So there's a small button which goes in the back button.
Where?
Just below the forward button.
Yes. Yes. So the title of the talk is Reimagining Computing Through Systems That Drive AI and AI That Shape Systems. Right. So if I break this title into 2 parts, I mean, if you consider AI and systems in all together, it has 2 categories. You can divide it into 2 categories. One is your AI is helping the systems, right? And the second is system is helping the AI. Right? There are 2 parts. So this part, the AI is helping the system. How can AI help the systems? See, the hardware designing procedure itself is a tedious procedure. It's not a very simple thing. It has many steps. You write codes, generates RTL, do synthesis, then placement, routing, and all that. And it's an iterative process. You have to do multiple rounds of verifications. So it's a tedious process. So can AI help there in designing the hardware? That could be one issue. So that means AI is helping in designing the hardware. I don't work there. My sir is there, Professor Chandan Karfa, probably his team is working there. So he could explain better after this talk probably. And then there are other area like AI is helping to the system. Like, see, you have many decision that needs to be taken in the system where you are executing a program. Say, for example, many requests are coming from the CPU side to the cache or DRAM controller, right? You have to take proper decision. Can we design some model and integrate into system and take better decisions so that the system throughput can be better, right? So that is also an area where the AI can help the system. So some of my students have started working there. But most of my work or my focus of this talk will be in the other part of the AI and system. But the system is actually helping the AI. How can system help the AI? Any idea?
Processing.
Right, by giving better environment so that the algorithm of AI can run efficiently in a manner that it can execute faster. The energy consumption is less, like that. So I'll be focusing mostly on this side, but the system will help the AI. Okay. So See, there is lot has happened till the this over the period. The computer was first about it. The name of the first programmable computer that has been developed or designed. It's the ENIAC during the Second World War. That's the probably the speed of that computer. Any idea? It could do around 5,000 multiplications or addition per second. Is it fast or slow? Of course, for us it's very fast, right? But compared to a computer, it's not that fast. It's relatively slow. You know the size of that computer was? It was like 1500 square feet. It's like a 3 BHK flat. Right? And that was doing that much of computation. Now, if you consider your phone that you are having on your palm top, that could do around 4 to 5 teraflops of operations per second. So that much capability we have received over this period of time. And how come this is possible? Any idea? The main reason behind that is the transistor scaling. You know what is that? Have you heard 5 nanometer chip, 4 nanometer chip, 180 nanometer chip? What are that? These things, nanometers and all that. You can assume it's the kind of size of the transistors. Right? It's not exactly the size, it's the channel length, but you can assume it's the size of the transistors. So if the size of the transistor is very small, 5 nanometer, how big is that? Any idea about the size of that 5 nanometer? Can you imagine what 5 nanometer is? If you take your hair, the diameter of your hair would be few lakh nanometer. So now think about the size of the transistor that has come right now. So because of that guy, this scaling from that size to this was possible, because every element that you are having in the system are made of transistors, be it a memory element or it could be a processing element. Everything are mostly made by the transistors. Right. So over the period of years, the evolution has happened, but the primary target of the researchers were these things: performance, power, and area of the system designers. These are the three main targets. What are they? We call it PPA: performance, power, and area. Now, we need better performance, right? So how do you measure a performance? There are many metrics to measure it. It could be IPC, right? Instruction per cycle. If you have better IPC, is it good or bad? Good. That means you process more amounts of instructions per cycle. It could be simple wall clock time, right? It could be the frequency of the CPU core. The higher, the better is. Right? So there are many parameters to evaluate the performance. And then the power consumptions, of course, we need a system which consumes less amount of power, and the area must be as small as possible. So these are the three main targets of the system designer. So yes, how do you achieve huge performance that you are gaining from your systems right now? Because you see, the systems are designed to solve problems, right? So if you see this whole stack, at the top of the stack you have problems, and you see the bottom of this stack, there are electrons. So it's basically the electrons are solving your problems. Right? So if I just give you electrons and tell solve the problem, will you be able to do it? Of course not, right? It's very difficult. Right? So you have layers of abstractions which is actually helping you in do that, and we need people in every layer so that you get a better system of it. So once you decide the problem, what's the next step? You need to find the solutions, the algorithm. To solve a particular problem, you have many algorithms. Right? You will probably pick the best one. So a particular problem can be solved in multiple ways. So you pick the best algorithm. So we need people who are actively doing research in this particular stack. Right? Once you decide that, okay, I have decided my algorithm, now I have to code. So you'll write the code in efficient manner. So that's coming the next part of the stack. Once it is coded, there comes the use of system software. Can somebody give me an example of system software? Operating system, and what else? Yeah. Okay. Compilers. Once you code something, you have to convert it into machine code, right? What is machine code? The instructions. So you write the code that will be converted into some instruction, and who will do it for you? It's the compilers. So once that instruction is being generated, the instructions are there in the exe file or the executable file, right? That's there in the secondary memory. The moment you load the executable file, it comes to your primary memory, right? So a program that you have written will now become a process. Did you understand my question here? I mean, a program becomes a process. That means you write a code, the code will be converted into instruction, and then you load it, right? Once you load it, that comes into your main memory, and your program becomes process. So you have multiple processes in this system, right? All of them will not get the codes, right? You have 4, 5, 8, this many number of codes. Probably you have more processes in the memory. So you have to take decisions. Which process has to be scheduled to which particular code? That decision has to be taken by whom? Who will take that decision? It's the scheduler of the operating system. So basically it's the operating system. So we need an efficient operating system to manage the processes, to manage the memory and resources and all that part. So this comes under this particular stack. So this whole cyan part is probably the software side of a system. Okay. Now this is very important, this yellow region, the software hardware interface. Any example of that? What is software hardware interface?
Drivers.
Software hardware interface. Have you heard ISA? ISA? Instruction set architecture. Have you heard it? Can somebody give an example of an ISA? x86, x5, MIPS, MIPS. So these are actually the ISA which creates a bridge between your software and the hardware. That is your ISA. Now what is an ISA? Is it a chip? Is it a software? Or what is it?
Instruction to execute the...
Instruction is your written, right? That has been generated by the compiler. Now what is instruction set architecture in the system? Is it a separate chip?
Why don't we put an instructor into that binary executable or something?
No. It's kind of protocol. I mean, when you design the hardware, it has been taught. If you have an instruction, how to interpret it. You have to understand the meaning of the instruction. Are you going to do an add operation or you're going to do a multiplication operation? That has to be told by the instruction. Right? So there are opcodes present in the instruction. You have to go to a particular bit location and take out the opcodes. How do computer know where is your bit code in the, opcode in the instruction? That has been taught when you were designing the system. So that protocols, how to interpret the instruction comes here. It's very important. It does not change very frequently, because if you change it, then your entire system software has to be changed. So you see, you can change the software. This is something which does not change very frequently. And underneath we are having the microarchitecture. So till this point, is it clear? The software side, and then the bridge, right? And then this entire green part comes under the pure hardware part. Right? What is microarchitecture then? You have CPU, you have memory. You cannot randomly put those things in a cabinet, right? You have to have a proper planning. Why I am saying so? Because you think of a case that, have you seen DRAM chips? DRAM chips are separate, CPU are separate, right? Why they are kept in a separate chip, in a separate area? One reason is CPU generated a lot of amount of heat. Have you felt it in your computers, in phones? Right? So if you keep those DRAM and that CPU with the same die, the heat will propagate from the CPU to the DRAM chip. Right? And if that happens, the working temperature of a DRAM is around 85 degrees centigrade. Right? So if more heat comes, what will happen? You have stored some data, some bits in the memory. You might encounter a bit flip. So you have stored something, your image, that can turn into some other image. I don't know. Something like this. So you lose your data. Right? So it's an architectural decision that you need to keep those things separately. Right? And then after this, underneath we are having the logics. Logics, you understand? What is logic? The logic of developing each and every module of the computers. Maybe the adder, maybe the multiplier. You can design multiplier into multiple ways. Maybe Booth multiplication is one way. There could be other multipliers as well. Right? That logics are made by the logic gates, AND gate, OR gate, and all that part. So this comes here. So we also need people here. And then after that we are having device. What is that device?
Transistors.
Right, the gates are made of transistors. Actually, you fabricate the logic finally. That comes here in the device part, and then beyond this is all physics. So that's how you actually solve the problem through the electron. So we need people everywhere doing active research so that you can get faster output from the system. Is it clear? The entire system state? The level of abstraction is very important, otherwise the things won't work. Okay. So if you see the bird's eye, yeah.
Sir, can you go to the previous slide? I have a question.
Yes.
If somebody wants to migrate from one architecture to another architecture, is it a easy way to do in this architecture?
See, this part changes very frequently, right? This changes very frequently, but this is something which does not change very frequently. You see, in every year you are getting an updated iPhone, 16, 17, 18, right? The hardwares are changing, so microarchitecture changes frequent, the software changes frequent. You cannot change this part because changing this has a lot of consequences. You have to change the compiler, you have to change the, many things are there, right? The entire software stack. Any more questions?
Like my question is, assume I am a programmer. I want to migrate to the microarchitecture side. Is it possible with this? Like, is it a hard way to do it or easy way to do it? Like with this architecture, if you are following.
Hard or easy means you want to develop a
I'm a
micro.
programmer. I want to transfer in the microarchitecture side. If I use this architecture layer of abstraction, is it hard or slow, or working process will be slow or hard?
I still did not get your point.
But
You are writing the code in the software and you want to transfer that code into microarchitecture. That's what the question is.
no, I am programmer. Assume. Now I want to migrate my career into this
Oh, you want to migrate your career, okay, into micro.
Not mine. I'm giving you the example.
Okay.
So if you are following this much layer of abstraction, it takes lots of time. So is there any way to?
You don't have to know every layer. I do not know the complexity of the algorithms. Probably the people who are working in algorithms will know it. I work in this layer. It's not
Between different layers don't require to.
No, not even. That's why the layer of abstractions has been created. It's very difficult to know everything by a single person. Okay, so if you see a bird's eye view of a system, right? There are processing element, there are memory element, and there are I/O elements, right? So there are lots of work that has happened in the processing domain. We have enough processing capability, right? But memory was ignored. But think of a case that you can process the data very fast in the system. But if the next data is coming very late, will you get a system which delivers you a better throughput? You will have to wait for the next data, right? So memory is important. You will see that the processors are quite fast. Processing is quite fast, but memory is the main problem. So this is Moore's law, probably you've gone through it. Moore says in every 18 months the transistor gets double. Right? So transistor gets double means you can pack more amount of computations in the chip. Right? And because of that, the transistor was shrinking, the frequency was also going high. So I have seen in my BTech time where today 2 GHz processor will come, next year 2.3 GHz processor will come. But you see nowadays since 2005 it's not increasing. Right? So we have reached up to a point because of some power wall problem. I'm not going there what is power wall problem and not that. Because of some problem the frequency is not scaling, and because of that we have reached to a point where you cannot take more performance from a single core. You cannot take it. You have reached to the threshold. So if you need more performance, you have to switch to multi-core system, right? Because of some problem, and you could not get more performance out of it. From single core, multi-core system has come. So now your CPUs are having multiple cores. How many cores have you seen in your CPUs? 8 cores, 16 cores, like that. Maximum how many cores can be there in a CPU that you have seen presently in the market? 64? I have also seen 128 core to 56 core CPUs, but not more than that. So is 256 core enough? I don't know whether it's enough or not. So if you can probably distribute your code into multiple threads and spawn those threads into multiple cores, you can take the leverage of 256 cores. But if you need more computation, say for example a very intensive AI algorithm where you have to do lots of multiplications per second. So in that case, the multi-core CPU won't work. So we have many processing options nowadays. First is the CPU core, and then you also know about the GPUs. Who are faster, CPU or GPU? GPU, not CPU. So then why do we keep CPU? Just remove it. Just keep, make our life simple, but have only GPUs.
GPU is faster for executing that for basic operation, but CPU is designed for overall average.
What do you mean by basic operation?
Like multiplication, addition.
That can also be very nicely done by the CPUs.
But also the power consumption. GPU consumes a lot of power.
I don't need to consume a lot of power. I'm happy with CPU. Why will I invest more power?
CPU is designed for like overall managing everything, but GPU can
Overall managing means?
overall managing systems like assigning tasks, scheduling.
So I'll directly assign by GPU. Why do I have to keep a separate?
In case CPU do the work, multiple works.
Okay, given a choice, say for example, I have a very nice computer shop and I want to sell a CPU and a GPU. Which one will you take from me?
If you
Take
have
GPU.
repetitive tasks, but in the large amount, you can go ahead with.
So basically it depends on the nature of the algorithm. If your algorithm has a lots of parallelism, you can distribute the task among 10,000 cores. Probably GPU would be a good option. But if you take one-on-one, one CPU core versus one GPU core, the CPU cores are bigger. It has a lot of computation capability. One-on-one CPU would win the race. You see the gigahertz of a CPU core around 4 gigahertz or something, but GPU cores are smaller. Right? So CPUs are still relevant, and the beautiful part of this CPU and GPUs are both are general purpose. Probably you could execute any type of applications there. Apart from that, also you also have many processing options like ASICs. Have you heard ASICs? What is ASIC? That is application specific integrated circuits. So those are dedicatedly made for a particular algorithm. These are very fast, these are very power efficient, but the only problem with the ASICs are those are application specific. That means it can run only, if you have designed for a particular algorithm, it will only execute that algorithm. Right? So if you have n number of algorithms to execute in a computer, will you plug n number of chips in the system? Is it even possible? So flexibility is an issue with the ASIC. So how do you choose your algorithm? That is a point of concern. So people try to choose those algorithms which are primitive to many applications. Say for example, a CNN maybe, convolutional neural network, widely used in computer vision. So all these applications who are using this CNN, if you make a ASIC for a CNN and all the applications who are using CNN as their backbone, you can offload the task to the ASIC chip. Right? So that way the flexibility problem would be addressed somewhat. So ASICs are fast, but the problem is you lose the flexibility. So what I wanted to say here, you have many processing options present in the market and everyone has a role to do. But as I said, memory is the main bottleneck. Processing can be done very fast, but if you get the data very slow, your overall throughput will go down. So in the next couple of slides, we will see why memory is important, where is the problem in the memory. Right? See, this is a very cartoonish pic of a system where you could see most of the elements are memory elements. You see, most of the elements are memory elements. Only these parts are the CPU cores. Right? So maximum chip area has been taken by the memory. Why there are so many memories? Not a single monolithic memory. We could probably keep a big monolithic memory instead of so many memories in the system. Why? Because the demand that we are having from a memory is contradicting. We have a contradicting demand from the memory. We want speed, we also want capacity. That's the problem. Think of a controller. If you have a bigger memory, main memory, that means it has multiple addresses, right? If it is having multiple addresses, the size of the address bit would be longer. Yes or no? So to decode that particular address which is having 16 bit and to decode an address which is having 64 bit, which one will be faster? 16 bit would be faster, but then you get a smaller memory, right? But you need bigger memory, so your demand is contradicting. So it's very problem for the controllers. You want capacity, you want fast. How come this can be handled? So to handle this, the systems are designed beautifully, right? In a hierarchical fashion where you have cache memory to give you speed, where you have main memory or the secondary memory to supply the capacity. Like this it is designed. So it's not a monolithic memory, rather you have a distributed memory present in the system. So you have lots of memories and data are traveling amongst the entire chip. Right. So here is yet another view of AMD chip where you have lots of memory. It's a chip from M1 from Apple. There also you have lots of memory, right? So what do we want from a memory? Zero cost, of course. If somebody gives me a memory device free of cost, I will be happy, right? So zero cost is the first requirement. Zero latency. What is zero latency? I want some data from the memory. Can I get it in no time? I mean, it has to take some time, right? But I want it no time. And that is why the research is going on. You're taking the data in 1 second. Now I need to take the data in 0.5 seconds. That's why the research is going on. So zero latency is the target. Infinite GB per second bandwidth is another target. Infinite capacity. Can I put every data in my computer? I don't need to buy any other SSD or something. I will just put things there. This would be very nice, right? If we would have got an infinite capacity, right? Apart from this basic demand, we also have additional demand from the memory. Memory means I'm talking about main memory, okay? I'm talking about main memory. So main memories are volatile. You know, you power down the system, the content will go from the system. But people are now coming up with technologies where main memory will keep the data persistently. It's non-volatile. Right? So non-volatile memories are coming. So it's a new demand. And then low leakage, you can ignore this for the time. So these are few demands. And you see, memory is a bottleneck. It's not invented in recent days. I have shown two back-to-back studies here. You see this study, this was done during 2003, right? So they have tried to design a microprocessor, a processor. The intent was they could execute 4 instructions in 1 cycle. That was the target. But when they end up having a microprocessor, they designed the microprocessor and they were running the application in it, they found that they could execute 1 instruction in 4 cycles. The target was 4 instruction in 1 cycle. What they achieve is 1 instruction in 4 cycles. So it's kind of 1/16 times slower. And that has happened because of this guy. Lots of L2 misses. Did you see this part? In the execution time, lots of L2 misses. What is L2? The last level cache at that time. Now you are having L3 cache. So if there is no data in the L2 cache, then you consult the main memory, which is a slower device. Right? So that means if you have more L2 misses, that means you are consulting with the main memory, so you are wasting time. So most of the times are being spent only by the data movement, not by the execution. So that study was done in 2003. It's pretty old, right? And the similar study has also been done in 2015 by Google, by the data centers workload. And they have also found the same thing. Most of their data centers are just spending time in sending data here and there, not doing any fruitful computations. So memory is the main bottleneck. So latency was problem. Energy was even more problem. Energy means the part over the period of time that is being consumed. Yet you see, to do an addition operation with 32-bit single bit precision, you need some energy, and you take that data from the main memory. The energy requirement is quite high. It's almost 6400 times higher if you are accessing the memory. So computations take less amount of time compared to the accessing the device. So memory is a problem in terms of latency as well as in terms of energy. How to solve it? There are many solutions. This is yet another study, I'm not going there. So how to solve it? One solution is near memory computing. Right? What does that mean? Means instead of bringing the data from the memory, can we send the compute inside the memory? Right? So we will process the data in the data's home itself. We will not bring the data from main memory to layer 3 cache, from layer 3 to layer 2, then to registers, and then we will process in the CPU. We will not do that. We will process the data in the data's home itself. That is called near memory processing. Right? So in that case, the traveling time of the data is reduced a lot. So there are two cases here. One is near memory processing, and the second one is processing in memory. There's a slight difference. I'll come to that point later. Okay, so that is one possible solution. There are many other solutions. People are actively working to reduce the memory latency and all that, right? Okay, so if you have to do near memory processing, you will have to integrate the processors inside the memory, right? What do I integrate? You have lots of memories in the system, like I said. It's not a single monolithic memory. You have many memories in the system. So what do we plug in? So you could plug in the processing element in the caches. You could probably plug in the elements in the memory controllers, anywhere, or in the SSDs, everywhere, right? So you have to select the proper space. Where do you want to target? Where do you want to plug the processing device? Right? So that is also point of concern for the researchers. Yes.
So my question is that when you are processing data in the memory itself, then the switching and jumping between instruction will also take a lot of means there are multiple addresses in main memory. So bit switching them also take a lot of time.
So it's a problem. So there are lots of challenges. See, in a system you have CPU, you also have GPU. Now you are saying, okay, I want to compute inside the memory. So many computations, right? So how do you supply data to everybody from the memory? Data traffic management of the data traffic itself is a problem. And then data consistency is also a problem, right? And you have to decide, if you have an application, should I use my CPU to process it? Or should I use my GPU to process it? Or I should offload the routine to the main memory, where I have already integrated some processing element, I should process it there. So that decision is also a kind of challenge, right? You have to decide on that, yes.
Does this also address the problem of energy which you were talking about?
Yes, because the data movement is reduced. So you want to set up a factory in Bangalore. So the raw material, would you prefer to bring it from Bangalore or from New Delhi? Bangalore. That will save your time, energy and all that, right? So it's kind of same concept.
But here energy depends on movement, or does it depend on compute? Like how much I am computing?
Both. Data transfer energy, data processing energy, it takes energy everywhere. So you're trying to reduce the data transfer energy, not the processing energy. Yeah. Yes.
So why are we not using this at the moment? Why do we have a CPU different from the RAM to begin with?
Why do we have a CPU?
The problem currently is that our compute is away from the RAM, right? So they must.
Why they are separate?
Yeah, why that's
Like I said, it's an architectural decision. CPU generates heat. If that heat is generated and sent to the DRAM cells, where you store the data, it's a capacitor. So that heat would affect the data. Right? So it was a very nice decision to keep them separate. But now it is creating another level of problem.
So with this will make our RAMs more heavy now. So because they will be holding the compute power plus the memory power.
Yes. So there are two things. One is you are having a RAM, you put a processor close to the RAM.
Right.
So basically processing is being done in a separate module, right?
Okay.
Not in the RAM.
Not in the RAM.
So that is near memory computing. And in-memory computing means you are having a cell, the cell itself is processing the data. It is storing the data as well as it is processing the data. That is near memory processing, right? So there is a minute difference in it. Yes.
So why does it make sense to do near main memory processing and all that? Because latency like usually comes from address translation.
Okay.
So why does it matter if we are doing processing and everything near
Latency does not only come from the address translation. Address decoding also takes time, right? And you see the off-chip link that connects the CPU with the main memory is very shallow. So you take data like 128 bit in one go. Think of a case that you are executing a very heavy neural network model and you are taking data like 128 bit in one go through the off-chip link. That will be very slow. Your pipe is very slow, right? So you cannot take water with heavy flow. So can I switch there? Got my point?
So will this cause incoherency problems?
Yeah, there are coherency problems that needs to be addressed. So people are actively doing research on that as well. Yes. Okay. So now you have to decide where to plug in. Right? You have. So mostly people have explored the main memory because that, like I said, the off-chip link that connects your main memory and so your cache, CPU, all are in the same chip. Your DRAM is in the separate chip. So those are connected through a shallow link. So this link is a problem. So people have tried to avoid this link and put the processing element in the memory. Memory means close to the main memory. Now there are many options in the main memory. You have 2D main memories that you are having right now. This DRAM, you have probably seen it if you have opened your computer or your laptop. You also have 3D memory. Have you heard 3D memories? No, right? Okay. So I'll give you a brief overview of that. How many time do I left? 10 minutes.
Yeah, overall 10 minutes.
Okay. So I'll go very fast. See, this main memory is being partitioned into this is called the main memory chip. This is called DIMM, dual in-line main memory module, right? So in DIMM you have multiple ranks. These are actually DRAM chips, right? So you could probably plug your device inside these chips, and if you unfold this chip, if you open this chip, you will see inside that chip you're also having banks. This is memory banks, right? Where you actually put the data. These are collection of cells, DRAM cells. So you could probably put inside the chip, outside the chip, near the RAM. Where do I plug? So it's a architectural decision that you must see. So I'm not going into detail of this DRAM architecture in the interest of time, right? You also have 3D memories. So I'm skipping this part, how DRAM works. I thought I will explain it, but let's move. So you understood, right? DRAM has multiple places where you could put the processors. That's the whole idea. You also have this 3D memory. You see, DRAM layers are stacked on top of each other and forms a die-like structure. This is a 3D memory. These are actually DRAM layers, right? This forms a vault, right? A kind of memory channel. And beneath this DRAM layer, you also have a logic base. This is not the memory layer, where you can actually, all the NOC circuitries are there, where you actually can put the processing element in this blue layer without touching the DRAM layer. So it's more convenient to use a 3D memory to plug in a processing device, right? So how system is actually helping the AI? So you see, I've tried to accelerate this CNN, a widely used vision model. So I've tried to make an accelerator for it. I've integrated those accelerators close to the 3D memory. Right? So if I plug the accelerator close to the 3D memory, what all benefits are there? One is data fetching or data storing time is very less. So I'm getting benefit there. And I am also using ASIC, which is the fastest while executing a particular algorithm. So this entire system that I have proposed during my PhD was a very highly efficient system. You see, I'm not going here. This is the system. So this is kind of 3D memory where you have DRAM layers, and in the logic base I said, I have integrated my designed hardware, this module Alumni, I have designed it and integrated multiple Alumni units. Right? So all the Alumni units also can parallelly execute. Right? So if you have a layer like this in a CNN, how do you distribute your work among the Alumni unit, right? So CNN, you know how does it work? So if you have multiple layers, so probably you can distribute one channel to one Alumni unit, next channel to next Alumni unit. So if you have a set of channels, maybe in a batch you can send them to multiple Alumni units, and all the Alumni units can parallelly work, parallelly execute. So you're incorporating some sort of parallelism here. And then within this channel, you have to do many dot products, right? So there are many MAC arrays within the Alumni itself. So those can also be parallelly run. So there are two levels of parallelism. One is all the Alumni units are parallelly working, and second is within the Alumni unit, you are having the MAC array, which can also parallelly work. Two levels of parallelism are here. And we have also tried to explore some sort of optimization. You see, we have analyzed the data. What essentially is being done within the CNN, you multiply the weights and activations, right? If you know, weights are from the model, activations are coming from the input. So we saw that a lot of this multiplication that is happening underneath are actually repeated, right? So this is the data. We saw that 30 to 40% multiplication are repeated. So should we do that repeated multiplication again and again? what could be done? If you are doing 2 into 3, you have already done 2 into 3 sometime before. Do you need to do 2 into 3 again? No. So what essentially we have done, instead of this multiplication and this addition, we have used 3 buffers. Right? These are associative memory. These are very fast. You can take out the data in one cycle here. And this multiplication operation is a multi-cycle operations. And there are lots of multiplication in the ANN. I mean any kind of neural network probably. So at least in CNN you have to do a lots of multiplications. So if your multiplication, one multiplication is taking 7 cycles, say for example, right? And you can take the data from the buffer in one cycle. You are actually saving 6 cycles per multiplication. If you have already computed it. So for example, you have already computed for a particular weights and multiplication, weights and activation, and you have already stored the weights and activation in the corresponding buffer. Next time when you send the weights and activations here for the multiplication, you parallelly send it to this buffers and say check whether you have already multiplied it or not. If you have already multiplied it, don't do the multiplication again. Directly take the results from here and send it to the adder, and you stop the multiplication, go to the next multiplication. So that's how you are saving at least a huge amount of cycles per multiplications. Right? That's our system. See, the software guy who was writing the code in the Python does not know about these things. He does not care about these things. He have probably called one function in the Python. Right? Underneath, you are doing these things. So you should make sure that the results is consistent, the accuracy is retained, right? That is also a concern, because you are not telling to the software guy that I am doing this kind of optimizations. So there could be cases like if you have already multiplied 2 into 3, next time 2 into 3 might not come. Exact 2 into 3 might not come. It could be 2.1 into 3.2. So will you say that those are same? So that decision has to be taken. So we have also incorporated some sort of approximation so that we get more amount of hit, and I can just remove the multiplications and get faster execution. So to get more amount of hit, we have incorporated a concept called masking. What is it? I'll come to the next slide. You see these two numbers are different, right? If you take these two numbers, these are different. But if you mask from the LSB part 5 bits, now those two numbers are 7. So what essentially we try to do, the activation and weight, we have tried to mask it up to 1 bit, 2 bit, 3 bit. The more you mask, you are actually tampering with the model as well as with the activation. So of course you will lose some accuracy over here. So you also try to analyze how much you are losing and how much you are gaining. You see we have masked 3 bit, 4 bit, 5 bit, and these are the losses. The losses are increasing, right? The more you mask, you get more hit because the data will become similar. You will be able to skip more multiplications, you get faster output, but you lose the accuracy. It's a kind of trade-off, right? And then there is also a trade-off, the size of the buffer, that also matters. If you have 16 entry, the hit rate would be less. If you have more entry, the probability of hit would be more. So we did that analysis and tried to find a design point out of it. What could be the size of those buffers? What should be the masking amount that is okay with you? If you do not even want a masking, you can totally stop it. If you do 0-bit masking, then also you are getting some sort of hit. Right? So you will be able to remove some multiplications even then. Right? So we get performance benefit, we also get energy benefit. Right? We have done analysis, you are tampering the data. Which one is good? Tampering activation is good or tampering weight is good? So we found that tampering weight is critical, you will lose more accuracy, at least in this setting that we have done there. In CNN with the, I think it's on CIFAR 10 dataset, right? So that analysis also been done. So essentially what we are trying to do, we are trying to design a system which will execute the CNN algorithm very fast, close to the memory. So it's close to the memory, you are saving on time, it's actually skipping some operations, so it will be fast. It is an ASIC, so it will even be faster. Right? So that way we got the performance and the energy benefit, and we have also designed the chip using the standard procedure using HLS, Vivado, and cadence synthesis. So there's another work where we, like I said, you can plug the memory element, I mean the processing element within the memory, right? So previous work I've shown that I've integrated it close to the 3D memory. This work you see I try to integrate the processing element in a 2D memory, right, close to the chips like I said. So that we have also tested. So the data flow matters a lot, right? Where you are integrating, which type of memory device you are using, that also matters a lot in achieving the performance and all that, right? So yes, so that was the work done by me during my PhD. My students are working now on this vision transformers, right? They are also trying to find out the optimization both in software end as well as in the hardware end, right? If you see this work to, so as to say this is a aircraft's image, I don't have to see this part of the image, right? So what essentially they are doing, they are trying to find the most important region of the image, right, and sending the according important token to the processors. They are not processing all the tokens. Instead of that, the token related to this part only, they are processing it, and they are getting good results. So I'm not going into these details. If you have any questions.
So I have one question. So after all this, your basic design, what is the kind of X time faster than the actual? So running things in on say normal processor versus your architecture with all this near memory computation, what is the kind of performance gain you are getting?
So we have got around 5 to 10 times better performance, but it depends on what is the baseline. If you are using a very fast GPU, probably your performance gain will go down. It depends on system to system.
So, are you still working on this, or the chip has already been made and it is now commercial?
By the way, it's not being fabricated and commercialized. There's a difference between academic research and the industry research. Someone has to take it up and then they have to do a lot of testing and then the fabrication is probably possible. Right? So these are done on simulators. So don't think that if you're designing hardware, you will have to take up wires around your shoulder and do the fabrication and all that. This is all coding. Okay?
So the research work is still being carried on.
Yes, probably how to design the chip in till the last, probably sir will say about it in the next talk. So you may be able to see it.
Okay. Any more questions?
Sir, you talked about near memory processing.
Right.
That's where you worked on, right? Could you like give a brief on in-memory processing also?
So in-memory processing is even more faster because the cell is processing itself, but it has limitation of computation. You cannot do a complex operation using in-memory computations till the point I have studied, but I have not seen that part right now. So probably you can just check the present state of the art, what is happening there.
What about heat?
In memory, no idea. I have to check on that. Yes.
Does near memory processing deal with the concept of memristor, like the
Memory?
memory resistance, memristors?
Memory registers, yes. Memory registers can be used to do some sort of near memory processing because you can use it like a crossbar array and you can do multiplications there.
Sir, can you please go to slide number 37? Yeah,
Yes.
yeah, previous one, 36. No, that logic diagram, the block there,
Previous.
Alan Miller.
It's going, okay. This one?
This
Yes.
one. Here, which is the intelligent unit that is deciding whether it has been previously computed, so that it will not do it again.
So we are checking for on every waits and activation, we are sending it parallelly to these buffers. These are actually associative memory. So in one cycle you get to know whether it's present or not, because you are parallelly checking in every locations.
Okay. So, but sometime that need to be erased, no?
Sometimes
So
you
how
get,
often it gets erased?
so it's the percentage, like 30% time you get it around, I'm saying,
Okay.
and even 70% time you have to rely on the traditional multiplication for that data set and for that setup.
So this is especially designed for this CNN.
Right. All ASICs are mostly for some particular task. Right? If you design ASIC for a CNN, probably it won't be able to execute a VID because the algorithms are different.
Maybe one last question, or maybe two.
So can you explain the masking part again about how that is helping us improve multiplications?
Is actually increasing the similarity of the data. If you see, these two data were different, right? Think of a case that this is an activation, right? Well, because of that, there was a mismatch.
What are these two data? Are we trying to multiply these two numbers? Or?
No, I'm not trying to multiply it. These are two different data.
Okay.
But if you mask it from the left hand side up to 5 bit, now those two data which were previously different now has become similar.
Right.
So think of a case that this is a weight. You masked it. So two weights will be same right now. So you are actually increasing the data similarity so that you get more hit in the buffers and you can skip more multiplications. So I'm doing this masking on both the activation as well as weights.
So when we need this data, actually we'll just add the offset later on. Is that something?
No, you take the whole data, but you are actually taking approximate data, not the exact data.
We are losing accuracy here.
You are losing accuracy. You want to stop it, you stop it.
Okay.
You still get the benefit.
Okay.
So it's a reconfigurable unit in this.
So we are increasing our computation on the risk of accuracy here.
It's a trade-off, yes.
Are there any major applications where you said masking for 10 bits?
You said masking for 10 bits?
10 bits, so you lose the entire accuracy, I hope so. So don't go there. I mean, you do not have any data, everything is zero.
Okay, I think in the, okay, sorry.
Yes.
So this, yes, so I think this masking idea, I see some similarity. I come from databases and data mining, so there is some similarity on that. Is it on? Yeah, okay. So we do the similar thing in databases also, when we try to sort of reduce the number of dimensions you want to scan over. So in the in exchange of better computation time. What we also try sometimes is that we want to. You are right now taking the input vector or the binary vectors as it is. But what we have sometimes tried is that we want to rearrange the bits so that the important bits are at the first and the less important ones are at the end, so that the masking has reduced effect on the accuracy. Of course, when you do rearranging, you are incurring some additional computation.
I see.
Any ideas of that kind have also been tried, or do you think
Can be tried. This is another way of doing the optimization, but I have to try, experiment with the data and have to check whether it is working on this particular model. It may happen that it is working on CNN, it might not work on VIT as well. So it's data dependent.
I think here MSB has the more values.
MSB you cannot hamper. You should not touch the MSB.
Sir, previously you said that it can disrupt data. We choose CPU far away from the DRAM. Previously you said, can this happen in this case also? Means it is very nearer to processor itself.
It is happening near to the processor.
So it can disrupt the data. Means
it is disturbing the data. You are tampering the data, right? But I am taking the data sitting on the memory. If you do not like, take the data in the CPU. If you do not like, take the data in GPU and process.
So you said that the heat would affect and the bit flip would happen in between. So doing some processing.
So yes, so this 3D is designed in such a way, those are different layers. So heat does not go that way. So the problem is there in the 2D memory, not in the 3D.
So sir, how would the data transfer go through the layers?
So it has through silicon via wires, which are very fast. So these modules are integrated close to those TSVs. You take the data from the DRAM through the TSVs there.
So the memory, like each memory component will be used in different types of computation or something, or?
Yes, you have multiple channels in the 3D memory. Probably you could use some channels for CPU, some channels for your thing. You can distribute it amongst you.
Like
so you have a whole controller that is controlling the things.
It's like an architectural design.
That's an architectural decision.
Okay, in the interest of time, I think we should pause the question. Let's thank the speaker again. He will be around. You guys can go and chat with him.
Yeah, thank you.
Token of appreciation. Okay, so okay, there is the top. You can. It is there. Check the folder. This one. Okay, so the next talk is machine learning for electronic design automation by Professor Chandan Karfa. Let me just quickly read the bio. Dr. Chandan Karfa is currently an associate professor in the Department of Computer Science and Engineering at IIT Guwahati, where he is working since August 2016. Prior to that, he has worked for 5 years as a senior R&D engineer in Synopsys India. He has visited New York University during the summer of 2019. He has obtained his MS and PhD degree in Computer Science and Engineering from IIT Kharagpur. His research interests include electronic design automation, formal verification, high-level synthesis, hardware security, and ML for EDA. He has published more than 80 research papers in very reputed international journals and conferences. He has received like a lot of awards, and few of them are Google India Research Award 2024, Google Silicon Research Award 2024 from Google, Qualcomm Faculty Award from Qualcomm, the Techno Innovator Award by India Electronics and Semiconductor Association in 2014, Innovative Student Projects Award from the Indian National Academy of Engineers in 2008 and 13, Best Paper Award in AdCom 2007, Best Paper Nomination in Asian Host 2020, Cases 2024, and VLSI 2025. And also Microsoft Research India PhD Fellows in 2028. So he is also a senior member at IEEE. So please.
Thank you, Anand, for the introduction. Thank you, organizer, for inviting me. And it was very nice to share the same session with Palas. We both joined IIT Guwahati at the same time, as a faculty and Palas as a student. And nice to see he's become a very proficient researcher now. So, what is this? So. Okay, so good morning everyone. I'll be talking about machine learning for electronic design automation. I will not ask the question how many do you know machine learning? Everybody knows nowadays. How many of you know what is electronic design automation? Okay, good. Some of you at least know. So for interest of others, I'll specify this talk like two ways. So I'll talk about what is electronic design automation first, and then I'll talk about more on how machine learning can help this EDA and what we are doing in IIT Guwahati in this ML for EDA domain. Right? So that's the kind of plan for today. Many of my initial slides is covered by Paula, so I'll skip them faster. So now in this we are actually living in an era of integrated circuits, right? So any device we are using, they are smart nowadays, right? So you think about your mobile phone, your washing machine, TV, everything is smart nowadays, right? And any system you're thinking about, it's a radar, it's a medical device, it's a grid, it's a aerospace, car. Yesterday there were a lot of talks on robotics by Rona. Everywhere they're smart and they're doing computations. So inside they have basically a chip, right? So which is basically called integrated circuits. So all this smartness come from these ICs, right? So what is there inside these ICs is basically transistors that you have already seen. So I will not go into detail of this. It's effectively transistor is nothing but a switch, right? So it basically has silicon layers. It has source, drain, base, and gate, and you try to put voltage from here. Either the electron will conduct from this or not. If it is conduct, it's switch on. If it is not, it's off, right? And then you can measure that value in a digital domain 1 or 0. That is how we can actually abstract the transistor behavior. Maybe electronics people will not be happy with this kind of explanation, but this is how computer science considers these transistors, right? So the detailed diagram. So effectively, if you connect this transistor in a combination, you will get some abstract behavior. For example, if you connect this 4 transistor in this way, you will get NOT gate behavior, right? So internally, you basically have your system as transistors, but they connect in a specific manner so that they behave like some logical way, and we can actually extract their behavior as and get not get and all, right? So this is what is there inside. So this quiz also most of the things Paulus has covered, so I will not take the quiz, rather I will give you the data. Human hair, we have almost 1 lakh, the width of this human hair is 1 lakh nanometer. Some virus, coronavirus affects us a lot, right? Which width is basically 100 nanometer. And a chip nowadays, which is we are using almost every mobile and all, it's 7 nanometer. So you can see the number, right? So our here, if you cut by width, it is something 1 lakh nanometer, which and then coronavirus is something 100 nanometers, which is 1000 times smaller than our human hair width, and the chip is 10 times smaller than even a virus, right? So this is the size of the chip. Sorry, the IC, these transistors, and let's see the counts. So how many here we have? Usually 1 lakh, not count my one, but others. How many virus can fit in into what is? Sorry, this is what we covered. So we have around 1 lakh normal here. If you think about a 2 centimeter cross 2 centimeter space, it's just like this, right? How many virus can fit in there? It's around 7.6 billion, right? Can you guess how many transistors can fit in there? It will be roughly 16 billion, right? So this is the number of transistors lying in your chip that you have in your pocket, right? And basically the mobile size is this much, but the chip size may be just this much, and that is doing all this computation for you. So this is what actually called this IC revolution, and it started 1950. First transistor was made in TI, and nowadays any chip you consider have billion number of transistors. So now this question is how do you build such chips, right? So it's not something that you can do it manually, right? This brief history of IC, I think Paulus has covered nicely. I'll just skip this. Basically, it's just to cover it lightly that your transistor size was shrinking as predicted by Gordon Moore in 50 years back, that every 2 years your transistor will become half. So what does it mean? You can actually put more transistor in the same space, right? And the Dennard scaling says that even if your transistor becomes smaller, if the area is same, your power consumption will be kind of same. So it means that you can do more computation with the same power. So that's the beauty, right? That's actually happened 40, 50 years, right? You try to reduce your transistor size so that you can put more manpower or more computation unit in your chip with the same cost. Cost in the sense with the same power consumption, right? But that hits a bottleneck, as Paulus mentioned, around 2006 or something, where you cannot make your transistor more smaller because of this heat dissipation, power heating, and all those things. So what happens? Then it can multi-core. But basically, instead of making one core very complex, you use multiple core and use them, right? But that also has some limitation, because you cannot just expect that if you make your number of core double, your performance will be double, right? It's not. There is a limitation of that, and that is captured by Amstrad law. It's basically says that after going from 220 to 56, after that you will not get any benefit, right? So no point putting more core inside your chip because of the synchronization, it's a data consistency issues and all, right? You have to move your data from one chip to another and all. So that will consume the benefits, right? So there is a limitation of do that, and that's why the era where we are is basically is the hardware accelerator. So instead of making a general purpose processor, you make ASIC chip, right? Which is basically application specific. I will have a chip that will do only the wireless transformation for me, something only do the image processing for me, something only do the CNN for me, something only do the Bluetooth connection for me. So and if you see the NOCs nowadays, it has hundreds of such blocks, right? So everybody is a very tiny chip, very less costly, and then is much faster than the general purpose, right? So we are is kind of in the era of hardware accelerator, and why I put this figure is just to show the evaluation, right? So now we have different profession, right? So we have engineer, doctors, and many professors. Even engineering, there is a computer science, electrical, mechanical, and all, right? So you have the specialized chip that way. So every chip is a specialized to do something else. So this is the kind of revolution we have. So the question definitely where I am more interested, my research focus on that is how do you build such tiny chips of billion transistors obviously manually, of course not possible. So we need automation. So what is the basic core idea here is that if I ask you to write a Verilog code that has with transistors, a billion transistors, it will take ever, right? You will never do this. So the core idea of this is that you basically try to develop your chip in higher abstraction level. So I give one abstraction already that if you connect 4 transistors this way, this is NOR gate, right? So this is one level of abstraction, that from the transistor level I get my circuit in the gate level. Okay. Even the gate level, the circuit size is too big, so we go one level up, and that is called register transfer level. So here I will not bother about what is the exact implementation of the adder multiplier. I will say that how the value of the registers get updated in every clock. So transfer of value in register in every clock, that is register transfer level. So here I will write R1 equal to R2 plus R3. So how do you implement the plus? That will come into the gate level. So this is one level of abstraction, right? So here you basically think about that how your circuits behaves in every clock, what operation you have to do, right? So that's kind of register transfer level behavior. And if you go more abstraction, you have the behavior, like where you can write your code C++, which is completely untimed, there is no clock there, it's a sequential code, and hardware is timed, right? And basically everything is running in parallel. So so now if you have this abstraction, so if you ask you to write a design in the C code, probably you can write in 1 hour. If I ask you to do the same in Verilog, in the RTL level, it probably need 2 days. If I ask you to do it in the gate level, probably it will take a month, right? So now this gives the benefit. You take less time, develop your design or specification in the higher abstraction level, and then you have this electronic design automation tool that will automatically convert them into the lower level automatically, right? This is how the entire chip design happens. And that's where this EDA comes into picture, right? So as I promised, I'll talk about the steps of this EDA. It's not one software, it has multiple softwares, and how they are actually performed, I'll talk about it very high level, okay? So as I mentioned, you have this multiple steps. So first is kind of high level synthesis, where you basically write your program in C++. You think about your convolution code is written in C++. And this tool will take that C++ code and do these operations and give you the RTL, register transfer level design, which is a Verilog, right? So it automatically does this, and there are commercial and free tool, which is quite popular, okay? Then it comes logic synthesis. It's basically, I talked about many abstraction level. All these tools convert from one abstraction level to the next level, right? So high level synthesis convert from C to RTL. Then logic synthesis convert from this RTL to gate level. I'll talk about that a little bit more. So what happened here? The first thing is the translation. Translation is understood that because you have a plus, you replace by a full adder circuit, right? 32-bit full adder and not. So that is translation. So you get your gate level design. But there are a lot of redundancies. So main challenge is the logic optimization. You identify all the logic which is redundant. How can you optimize your circuit? That is called logic optimization. And that you probably have heard Cohen-McCloskey Carnot map, but those are good for theory, not for practice. So there are a lot of heuristic approaches are there, which actually do the logic optimization for you. And it's a complex problem, right? And then comes the technology mapping. What it happens here? Here you have this netlist, but your target architecture may not have all these gates, right? It has a very specific type of gates. You probably heard of ASIC and 45 nanometer chip and all, right? So the technology library have a very specific set of gates. So now you convert your logic in terms of only those gates. And it's a pattern matching problem. So you identify a pattern in your circuit, which is basically, you can think about a graph, because each node, each AND gate can be a node, right? And the connection is the edge. So you can think about your circuit is basically a graph. You try to identify a subgraph and try to replace that with a pattern that is there in the technology libraries, right? Again, that's an NP-complete problem, a computation hard problem, okay? So then you get the technology map netlist. Then you do the physical synthesis, where you basically actually place all the transistor, all the gates. You first convert the gate into transistor. Again, that is obvious. And then you place them in an entire chip, because you have to now place every chip in this layout. You have to make the actual corrections, and that consists of these steps like partitioning, floor planning, placement, routing, and compaction. So I'll show you by graph. So this I'll skip. This I have already talked about. So this physical synthesis is one of the most complex process, So you have a very big, because now your circuit is grown up. It's not in C or RTL. Now you have the net list, which is million of nodes, right? So anything you do here is very complex. So that's why the primary approach of doing this is divide and conquer, right? So in computer science, whenever we don't be able to solve the entire problem, we break into part, try to solve the small problem and combine them to get the better solution, right? Of the overall solution, right? So we do the same thing. So I have to do the placement of the entire thing. I break them into small component. If this is big enough, I'll again break them into smaller part and hierarchically bring them to a small component which I can handle, right? So this is how I solve. So this is called partitioning, and then you have to place them. So again, the partitioning has this problem: where do you cut? Where do you partition, right? If you partition arbitrary places, number of wire crossing, those has to be routed, right? You have to make the connections actually. So your objective of this partition is that how do you cut this circuit so the number of wire going here is minimum. Again, it's a very hard computation problem, entry complete problem. So that's the partitioning. Then you place it. When you place it, you try to place the node that have connections, right? For example, if you try to place these gates here, your wire length will be 10, but if you place in this order, the wire length is 12. So same circuit, wire length is different because if there are two nodes are connected, they should be connected close by, so that your wire length is reduced, right? Again, this placement is a complex problem, and then just to show that if your placement is random placement is bad, lot of wires, but if you do a good placement, your number of wire length is less. Just the same diagram again, and then you have to make the connections. You have placed the designs, and you know that I have to make a connection from this to this, so I cannot make a diagonal connection, right? So you have to go x-axis then y-axis, right? So again, you have to, your objective is to there are multiple paths, so to connect this to this, you can come this way, you can come this way, you can come that way, and so many ways. You try to make the path so that your length of the wire is minimum, right? So this is what is called routing. So by all those things, you get the layout, then you do the fabrication. It's a very complex process where you basically, your circuit become physical chip, right? After fabrication, you also need the verification here, because once you convert a C code to RTL, there may be bug in your tool. You have to make sure that your RTL is functionally equivalent to the C. So you need verification for that. Similarly, for every step you need to have lot of verification things, and I think verification effort is more than the synthesis effort nowadays. Okay. And you also need test. When you make the chip, physical chip, your actual circuit was correct, but because of some manufacturing defect, there may be some connection happen like this, some open circuit, your chip will not work. Your circuit functionality was correct, but chip has some manufacturing defect. Okay? So we have this domain called VLSI test, which basically try to identify, is your chip faulty, right? Is there any manufacturing defect in your chip, right? So that's called VLSI test. And then the security comes into the recent time. So here, if you see here, you have this design, you do this logic synthesis, then physical synthesis, you get the layout, you do the fabrication, you get the effort, then you do the packaging, you do the test, and you get the IC. So this is the overall flow. But none of the company except few in the market have the entire flow, because it's a very costly. The fabrication is very costly, the testing facility is very costly, right? So you do not have everything on your own in-house. So you have to rely on third party, right? So that means you make your chip, which is a lot of intellectual property. You have done a lot of innovation to make your chip very fast. Now you give somebody to test it. He can copy it, right? And you can use it, right, in the black market. Similarly, it can take the after fabricated chip also, they can the reverse engineer and get the layout, right? Because there is no protection. So how to make sure that your chip, which you have to give it for testing, you have to give it for fabrication, they cannot use it, right? That is those threats called reverse engineering, IP piracies and all, and you have to stop them. Okay, you cannot make sure that somebody, your rival, can get it and sell it in the black market half of your price, right? So these security threats also come into the IP supply chain, and that's one of the major concerns, right? So if you see the EDA in a nutshell, you have the synthesis tool which do this conversion. You have this verification tool that makes sure that there is no functional bug in your design. You have this testing to make sure that your physical chip is working correctly, and you have the security concept, right? So if you think about the entire domain, this is what is your EDA domain is. And semiconductor domain conveys of the packaging, manufacturing and all, right? So my first part of the talk is over, where I talked about the entire EDA flow. Any questions on that? You get an idea, right? What is happening there?
So how we do model checking if the code we written C is similar to what is?
Yeah, so model checking is a way of verifying your system. You think about you try to check your C program is correct or not, right? So from C, what I will do internally, I create a model which is a crypto structure, which is basically a state machine that represent your program states and their transitions, and you have written the correctness property, right? So that you say that x will be always greater than 0. If x greater than 0 implies y will be greater than 0, something like this, right? And there are temporal property. When you go to the circuit, use temporal properties, and that in this clock your signal 1 came, within 2 cycles your signal 2 has to be asserted, right? So this kind of temporal decisions also there. So you write those property in a model checking things, and then you give it to the model checker. It will check whether this property is satisfied by this implementation or not, right? So this is how things work.
So EDA works at the level of which abstraction? C++ to
All are
RTL
EDA.
or RTL to
All are EDA. It's basically EDA actually convert one higher abstraction level to the next abstraction level, right? So your high level synthesis tool, which is also EDA tool, which convert your C program into RTL in Verilog. You have logic synthesis tool, which convert your Verilog RTL into gate level Verilog. And then you have physical synthesis tool, which will take the gate level design and convert into layout, GDS, right? So all are EDA tool. Even the verification tools are EDA, all the security measurement tools are EDA, VLSI test tools are also EDA. These are all combined in the EDA domain. Okay?
So do we do verification and testing at every stage of the synthesis?
Yes. So if you see my diagram, I have shown that, right? Yeah, this one. You see, whenever you do this chief definition, you have to make sure that your system is correct. Even your specification is correct or not, you have to make sure, right? Then whenever you do this layout, you have all this layout synthesis, circuit design, you have all these tools, and there are a lot of methods. I mean, one of my focus of research is basically formal verification. I did my PhD on formal verification. So I will try to use mathematical model, right? So model checking, theorem proving, to verify the correctness of your implementation.
OTPs are used in
Yes.
So what happens when there is a defect in one of the chips?
You have to throw it out.
Entire chip or only that part can it be?
Only one. So in a wafer, there may be 1,000 chips you have fabricated. 5 of them is usually yield is 80%. If your 80% chip come correctly, you will be happy. Because it's so small, right? 5 nanometer, 7 nanometer. There will be some manufacturing defect. So that's the kind of challenge of the fabrication, that you make sure that your yield is at least 80%, so that you are actually only throwing out 20% of the chip.
Can't we exclude only that part which is defective?
Yeah, we do that, right? So what I'm saying that if you see this diagram, so the wafer is this, right? Each cross box is one chip. So within one wafer there may be 1,000 chips there, and maybe 200 of them or 100 of them is faulty. So we just throw them out. Others I'll keep it. Because I have to cut them, right? And I'll get individual chip. Not the entire wafer, obviously. They will be bankrupted in few years, right? Any other question? Yes.
Instead of doing that, can we do binning process?
Sorry?
Binning.
It's so small that it needs advanced mechanism. It's not so easy. I'll talk about more in the latter part of the talk. Any other question? So you are familiar with the EDA now, right? Because now I'm going to talk about ML for EDA, and if you do not comfortable with the EDA, you will not understand or appreciate the second part of it. And go ahead. Okay. So as I mentioned now, everywhere, every domain you take, it's an automotive car, it's AI chip, what Wallace talks about more. Everywhere you have finally the transistors or the semiconductor, right? And if you see the market, in 2021 it's $600 billion, and it's going to grow only. There is no end of it, right? Everybody needs chips. And if you remember, during COVID time, car was not delivered because of the shortage of chip, right? It's not about mechanical parts. Because of the chip that is there inside the chip, that was not coming from the TSMC, right? So everybody needs chips, and it's a huge market, right? Because it's a market, the EDA market is also growing, because without EDA, chip industry is meaningless, right? They cannot develop a single chip without EDA, right? So the amount of chip you need more EDA. Okay? And this slide I want to specifically highlight. If you see here, the verification engineer have more effort in the chip design process, because the complexity is growing, number of transistors is getting more into the design, so your circuit is become complex, you need more verification effort. So the cost for chip design, design engineer effort versus verification engineer has more effort in the interflow. Okay. So I will now move into this next part. So when you do this synthesis process, what is your objective? You want to get better Q1, quality of results, right? What is Q1? Either you try to make your area less or power consumption less, or you want to make your chip faster, right? So it's called PPA, right? Power, performance or area. So you want to make sure that when you do synthesis, I convert from C to RTL by RTL has less area, right? Compared to other versions. So the objective of this entire EDA design automation to improve the Q1. But as I mentioned, when I specifically go through these steps, I almost every slide I say it's a complex problem, it's an NP-complete problem, it's a complex and hard problem, right? So most of the tasks in the EDA flow are actually NP-complete. What does it mean? Anybody know what is NP-complete? It does not have a polynomial time good solution, right, or optimal solution. So what it does here, it basically does heuristic. So people have experience, they know that if this is the circuit, if you move this modification, circuit will have less area. If you do this modification, your power will improve. This is just come from experience, years of experience, and that is how the EDA tool is working now. You have to realize them, they all have heuristic inside. All the synopsis cadence tool, they have heuristic to do the partitioning, heuristic for routing, heuristic for logic optimization, everything is heuristic, and that actually is something called known scenario. We know that these are the scenario is known, and in this case, if you do this modification, circuit will work better. But what about unknown scenarios? It may not work, right? So that is where ML can help. I'll come to that. Just to show you this, there is a case study that if you take Cortex A510 project, the search space is basically 10 to the power 25. So this is the number kind of search space. And if you run the one-time synthesis tool, it takes 3 hours. And ideally, it has to run 10 to the power 3 times, 1000 times to get the optimal result. So what is the problem? I do the synthesis and I found that my area is not fitting into my target area, right? Or maybe I want 200 megahertz, but it becomes 120 megahertz, right? I want to increase the speed. So then what design engineer do? Open the report, check, oh, this is the problem, they apply certain optimizations. The tools give you pragmas. You apply this, that, you do retiming, you do some clock balancing and so on, and then you again synthesize. And this is a multiple time iterations, and that is where this human effort comes into picture, right? And that takes almost 2 weeks just to get a synthesized design which meets your target Q1. You can understand, everything is automated, but still it is that much of time. So what will be your interest? You try to reduce the runtime, right? So you want to get a better Q1 with faster runtime. You don't want 2 weeks to just synthesize the design, because then you'll miss the bus. Somebody else will come and their chip will come earlier than your chip into the market, right? So the entire objective of this flow is that you try to get a better Q1 with faster turnaround time. And that is why machine learning can help a lot. How? So I'll talk about that. So this is I already talked about, that the conventional tool knows the known recipe. The recipe is the optimization sequence that is needed to get your chip optimized. Okay, that is called recipe. So in the case of syn recipe, that will do well, but the tool may not do good or maybe do very bad for unseen scenarios, right? And that is where the machine learning or AI assisted tool can come. They can learn from the existing run or the data set, and they can take a decision that will be much better than this heuristic solution, right? So that's the kind of use of AI ML into this EDA flow. Okay. So there are 3 directions of research in which people are focusing recent times. The one direction is basically the AI assisted tools, where you try to predict. So I give a design, you basically tell me this will be the, if you do the synthesis, this will be the expected area. And if the accuracy of your predictor is 95%, 94%, you will be happy, right? Or you give a design, you give a recipe. Recipe is what? Your optimization sequence. and then you tell that this will be the power when you optimize the design with this recipe without do the synthesis, right? So I have now a predictor where I will give the design and a recipe. I will not do the synthesis, but I will predict that this will be my area if I apply this optimizer. So then I will save that time, right? I don't need to synthesize and check, oh, I do not meet my area, right? I can just throw away some recipes which is not good for my design, right? So this kind of predictions are quite popular, and also you can do recipe synthesis. I can use this predictor in round, and then I can apply an RL technique, which what can do? It can just take a recipe, do some cost calculation, and then either keep the recipe or try to generate the next recipe, so that finally you give a recipe which is best for this design, right? So all this area kind of work happens in this domain. There is one level is the GPU accelerated computing. It's another domain of very active research here. What happens here, as I mentioned, all the tasks are NP computer hard problem, right? So it's optimization problem. So how about you do this rethinking this optimization problem as a neural network thinking problem or gradient descent problem, right? And use GPU to solve this problem, right? So you map this partitioning problem as a optimization problem and solve in GPU, right? So that's a completely different way of thinking how to actually do the optimization in the EDA2. Okay, so that's a different second thread. And the generative agentic AI or LLM also is very useful in this domain. And there's a lot of research where they try to identify the kind of small task, right, or not so critical tasks that can be automated with LLMs. Okay. So this is the third vertical of the work where this ML for ADS. So we work primarily on the first and the third one. So I'll talk about more about what our work. So this is another way of looking into this. You can apply all this ML as well as the agents into the EDA flow, and your objective is kind of no human in the loop design. Okay. So just to give an idea that you can have multiple design, you have timing data, you can create a ML model, and then you use this model inside the tool. Okay. And you can have this recommender, optimization, and predict. So these are the kind of use of this ML tool, right? If you look into the overall work in the worldwide, so a lot of good universities already working in a lot in this domain. People are working so color coded. So you think about that GPU acceleration, NVIDIA is working. LLM only work, Stanford, Hong Kong University, they are working on those. Agentic AI is LLM where, which is agentic AI, so NVIDIA, there are a lot of universities are working. And I mean, I can say that not many in India works on this area, but it's a very, very important area. And I think in my knowledge, only our group work on this ML for area in India. So just to give you context, how LLM can be useful here. If you think about the team hierarchy in a design house, right, like Samsung or other companies, there are a lot of junior engineers. They are just freshers from college, right? And there are some intermediate experienced engineer. Then you have the manager and the expert, right? So what happened? These people does not know anything about the entire SOC, but they are given very specific small tasks without knowing what is going to be use of this and all. They do this with the guidance from their manager, right? So the context, in this context, we can actually replace some of these tasks with LLM because some of the tasks is very trivial. Okay. So I'll show you some examples. These are some of the area where LLM can be useful. So I'll now move into our work. So in interest of time, I'll cover as many as possible. But I'll give you the core idea what it means. So first one is how LLM is helping HLS. So if you read the title, I have written friend or foe, right? So there are a lot of research nowadays on generating Verilog directly from English classification using LLM. You will see hundreds of paper nowadays. So, and also this HLS also do the same task, right? That's C2RTL. It's also generating this. So is it something that LLM will replace HLS or not? That's the question we asked, and we do some analysis, and we found that the LLM cannot handle bigger design. They just do some small design, so they cannot beat HLS, right? But can they help? And we found out that LLM can be a great assistant for a HLS to generate a efficient hardware. And just to give a context, so if you give a C code to the HLS, if you give to the HLS, it will give the RTL. So in high level, the salesperson will tell that you give your C, you will get the RTL, right? They will not talk about manual effort. But if you go deep, you will see there are a lot of manual effort here. First of all, your C code may have some construct that is not synthesizable, just like function pointer, right? Or malloc, dynamic memory allocation. So you have to make your code modify it to make it synthesizable. That's the first task. Then when Paula was talking about convolution network, you have 6 next state for loop, right? So you have a very complex task. You may not be able to do that efficiently in hardware. You need to do probably some source code optimization like loop tiling, so that it become your memory access become more efficient, right? So those kind of source optimization you have to do. You can also have to do some pragma optimization. You have to do pipelining here, you have to do array partitioning here and all. You have to do that. So whenever you do not meet your target, you go back and you do all this business. And this is manual effort, right? It takes a lot of time. So what we have tried that, we try to use this agentic AI, try to make this process automated. So we basically able to develop the tool, but I just use the HLS tool in background, and whatever the source code optimization, making it synthesizable, apply pragma, everything automatically agent decides. Whenever it does not meet the target, the report comes back and it applies different kind of optimizations, and it's a completely no human in the loop design, right? Entire manual effort is removed. And some example of that, I can skip this source code also. Here I just tiling, right? So this is a 3 nested loop. I make a tile of 4, and it's actually improve the locality of reference. I hope you know that. Pragma insertion, like you want to partition the array, you want to apply some pipelining, unroll and all, HLS can do that for you, right? And doing that, I can show that, so I have taken some machine learning applications, and we are able to improve the speed by 20x times, 2600 times, some other number, right? So it's automated, right? So in baseline where no optimization versus after applying all these optimization automatically by LLM, I am able to achieve this much, okay? To give a comparison, there is a tool called HLS for ML. Out of 10 cases, 4 cases our LLM assisted HLS beat a specialized tool which can generate ML accelerator, right? And some other cases where we could not beat them, if you see here, their area is 11 times of the baseline, which are only, we are actually reduced by 80%. So although they maybe achieve the speed, but their area is explored. So you cannot build that chip, right? Although, so those are also cases where they develop or basically chips that cannot be fabricated at the end, right? So what I'm trying to say here is that automated tool without any manual effort doing good, right? In that context. So this is one of the LLM work, but I'm more interested in this work, which is basically ML for logic synthesis. In logic synthesis, what you do? We basically take the register transfer level design, convert into get level. The steps are this, right? So you first generate the optimized get level design, and this is the steps of technology mapping. So what it does, it basically, so as I mentioned that you have to map this get level design into the technology library. And it's a pattern matching problem I talked to you, right? So what you do, you try to find out a subgraph from this node which has the same pattern in the technology library, right? And I don't know what pattern will be matching there. So what we do, we generate a lot of cuts. I can generate a node of 3 nodes, 4 nodes, 5 nodes, and all, right? That those are called cuts. So for each node, I create all possible cuts. Then I have a cut set, and I have the library pattern, and then I do a Boolean matching, right? So I basically generate all possible cut, and then I prune some of them, and then I model this cut as a truth table, and then Boolean matching is between this pattern to the pattern in the netlist, in the technology library, right? And then you basically get, say this part will be by one technology node, this will be mapped by another technology cells, and so on. So this is what happened inside the technology mapping, okay? So what we did here, first thing, the major bottleneck is the number of cards you produce. The ABC tool, which is an open source tool, we have seen that for each node, it generates 250 cards. Now you think about that, your design has 20,000 nodes. You can understand number of cards it produces, right? It's huge. And your runtime depends on the number of cards you are handling, right? So the first task we did is basically we try to bring ML and we develop a card classifier. What it does, it just given a card, it will tell whether this card can be implemented by a technology node or not. It's a yes no answer. You give a cart, it will tell no, it cannot be implemented, right? And we found that 85% of the carts are useless. When you generate automatically, 85% of the cart is non-implemented. So by just doing this ML classifier, we are removing 85% of the carts, right? Then we develop a delay predictor which will tell for this implementable cart what will be the approximate delay. Okay, I use that information when I do the actual mapping. So using these two ML model, we developed the tool called Leap, which able to show that 50% of the cart is reduced. Right? This is the cart by ABC. This is the number of cart we have used. So I can roughly tell that runtime will be improved by 40 to 50% of the tool with this kind of information. Right? Detailed result. Forget about everything. You show this for 20 designs we have done. 51% of the cart has reduced. We do not touch the area. We have improved the delay by 2%. So we are using only some carts, but we are giving better results with fewer carts. Right? So that means this ML actually helping make the runtime faster, giving the better keyword. Right? So that's the kind of work we have done. Then we found this problem of federated learning here. What is the problem here? That Synopsys developed the tool, right? But they do not have any design. Designs are with Intel, Qualcomm, Samsung. So they will not give that to Synopsys for training, right? Because that's the proprietary things to them. Then how Synopsys will develop the ML model and put into Day-2? Well, it is not possible, right? So yesterday we have a talk on federated learning. So we take the same concept that let's develop the model and give it to the design house. They'll let them train there, and then I'll do the aggregate, right? So I do not share that design, but I train model in the design house and I'll combine them, right? So this actually, because I have now diversified the designs, this will reduce the cart by further. Right? That's the objective. And if you see here, this diagram perfectly fits it. The idea here is that if your cart is increases, your area value will reduce. That is by ABC. This is a real data. It is not fake data, right? So we have run for some designs. When you increase the number of carts, your area has reduced in ABC. But if your carts is improved, I mean number of carts increases, runtime will also increase. Right? That's not the objective. So we achieve with Leap this much, that we are able to get this area with this many carts, which for this ABC need this many carts, right? This much area they will achieve with this. So this is the advantage Leap has achieved. With FedTM we want to reach here. We want to get further reduction in the carts, but I want to maintain the same area values. That's what we are going to achieve with diversify the designs. Okay? And that we have done, and we actually get it. So if you see here, this is the number of carts that is FedTM select, this is the Leap, and this is the other comparative tools. And you can see that it is less than the Leap as well. Right? And we have actually reduced the 23% of carts as compared to Leap. And we are achieving the similar keyword that I told you. Right? And just to show the runtime, this is the runtime versus ABC versus FedTM. You can see that it's kind of half, right? So 4.12, 2.78 and so on. So the reducing ABC actually, the cards actually shows that it can actually make your tool faster, right? This is one direction. Then we come up with this idea that so far we are talking about the technology library, we are talking about only one technology library, okay? But every design has their own technology library. So you cannot think about that everybody will use the same technology library, right? Then if you train one model in one technology library and try to use in other, it will perform very, very badly, right? Here is the data to prove that point. So we have developed that cart classifier on all these models in NAN45 technology, and when you predict it, they are quite close, right? It's very close. You see the green versus green, they are very close. Actual value and predicted value, they are close. But whenever you go use the same model in a different technology library called Skywater 130, you see here actual value is this, your predicted value is this. It's basically doing nothing, right? And it's going to happen because 130 nanometer the transistor size is bigger, so area will be much more, delay will be much more. So you cannot compare apple, it's not apple to apple comparison, right? So whenever you want to try to do this across technology library, this kind of method it has a bottleneck. Whether you do Leap or FedTM, they have a bottleneck. So what we have done, we basically bring the concept of transfer learning, where this is the model architecture which I can skip. So what is the basic concept? You have this model for one technology library which is already trained. Now if you have a different technology library, you take the design, you create some small set of recipes, right? Some small data sets, 30 sets, right? And you retrain the model again, right? Instead of the complete training, I'll do training for a small portion of the data. And once I do this, I get a model which is compatible for your technology library. And then what I did is basically I use this and use a simulated annealing framework where I keep generating recipes, give to the model, it is predict the keyword, and then simulated annealing, choose the different recipe, and finally it give me an optimized recipe for this design, right? So what I did, take the AIG, I put it here, I get the recipe or the optimization sequence that can give me the best power or best area for this my design, right? And then I use into the ABC flow to get my optimization. This is our metal flow, which is submitted in leading conference recently. So with this, we are able to achieve this. So you can see here, you can see that this is the same results that if you try to do in a different train on one library. So we have trained on 945 and predicted on ASAP and 180. GF180, the prediction is bad for other technology libraries, right? So this is, I have already shown you the proof. But once you do this transfer learning, the accuracy comes back, right? So initially the accuracy go to 69%, 69%, but after retraining, it's again become 94, 95, right? Which is close to the original one, right? And it's happening across libraries. For 130, it goes to as bad as 21%, 42%. After retraining, again it becomes 94, 95, right? The same goes for JBird. So the transfer learning works across libraries, right? And with this, we are able to show that our tool is now working across libraries. So you don't need to go to all data, but if you see the green is the best result when you compare our versus ABC. For across libraries, most of the green is our column, right? So it shows that our tool is doing better than ABC across libraries. And we are internally use ML model inside, right? Instead of ABC, which has a fixed set of optimization sequences. So I'll now move into the verification assertion generation, is another set of work that you do. So if you see here, you have the design specification. Verification engineer will write the properties, write what your friend asked me, and then design engineer will write the Verilog code from this, either through HLS or by yourself, right? And then once you have, then you have to say that whether these properties satisfy here or not. If not, you say that there are some implementation in your bug, you go back and then you go back and you modify it and this loops goes on. Right? This is the verification flow, right? So we ask, can LLM help here? Okay. So the major task here is that you have to generate these properties from this specification automatically. But it's a English language text, right? And LLM is good in language, it's a language processor. So it should do that well, right? So we try to use LLM, ChatGPT and others, try to generate these properties from here. That's the first thing we do. But what we found that, so this is our first work, Cheetah. We give this specification to the LLM, we generate the assertions, but these assertions are generic assertions. It just says that there is no design specific information there, right? There is no register name, there is no clock name, there is nothing, right? It's a generic properties. So then what we do is basically we say that you have to show your Verilog once to this LLM that, see, this is a property, but you need to verify this into this design. So let's remap this property into this, for this design. And LLM will do that, right? So this is the overall flow. And we actually did that. And then we modify that this mapping between the Verilog into specification, we, in the Cheetah work, we did it manually. And that we automated in the next version of the tool. And then we come up with the Sangam, where we basically say that, look, if you just do one go, your properties will not be good enough. And if you want to say, give a control like I want to generate certain properties corresponding to these signals, that cannot be done. So what we have done, we do the Monte Carlo tree search to identify signal specific properties. You tell me that you give me these properties for these signals, this tool can automatically give you the properties. Okay? And good news is that when you do this, see the coverage. So we generate for certain open source designs, coverage is 90%, 92%, 83%. And these are generated by automatic tool, right? It is not by experts. And we found that there are, for this RB timer and all, we generate certain properties that is not there in the open source library. So we are able to identify certain properties which even an expert did not think about, right? So that's the another direction of research where you work. I think now I am in the end of my talk. So there are a lot of good conferences in this. If you are interested to work on, you should look into these conferences. These are extremely recent work being published, and just to show the relevance of ML in the ADA, there are two conferences came, this LAD and ML CAT. These are just present the work for how ML can help EDA. All the work that comes here. This is LLM for EDA, and this is ML for EDA in general, right? So please follow this kind of research. But I have noticed that many of them are CSE. Some people think that electronic design is not for CSE student, right? I am a CSE engineer, right? So there are a lot, actually I think CSE has a major role in this flow. I think you are now appreciate this slide with my presentation. You need a lot of people who knows ML, who have a good coding capacity, who know the formal methods, formal verifications. Everybody needs in this domain, right? You need this kind of skill set. You should have good data structure algorithm knowledge, excellent C++ coding. You should have formal method background and some basic knowledge of digital design. You cannot say I don't know anything about hardware, right? You have to have. And then machine learning is a boost. These are the major companies. I want to conclude with this that you probably heard of this in India semiconductor mission. So with this, now India is going to build chips, right? We are getting basically fabricating fabrication lab in India, 2 in Gujarat, 1 in Assam. We are now going to build chip in India. It's going to happen for the first time, and I think by 2026 this industry will be functional in another year, and there will be huge opportunity. Right? You need all the additional workforce to develop chips, right? And to help that, Government of India come up with this nice plan, C2S. All the commercial tools are available to you. You can just register here. You will get all the chip, all the software from any India companies for free for you. Right? You can develop your own chip for free, right? So I think you should take advantage of this. There are a lot of other initiatives by Government of India so that you can create skilled manpower in this domain. And to conclude, there are a lot of potential of ML and AI to change this EDA flow, the way we see and the way we develop chips nowadays. And I hope some of you will take this potential as an opportunity. Thank you. So any questions? Yes.
So you're using ML and
So you were using ML and LLMs and such technologies to make EDA automatic. But isn't there a trade-off when it comes to the power consumption, because that's a hot topic today?
Let me just find your bio. Sorry. Okay, so after the coffee break, we have another exciting talk by Professor Anupam Sanghi from IIT Hyderabad. The topic of the talk is, title of the talk is From Static to Strategic Rethinking Testing and Benchmarking in Data System. So seems like a very cool title. Here is the bio that I would like to read. Anupam Sanghi is an assistant professor in the Department of Computer Science and Engineering at IIT Hyderabad. Before that, he was a postdoc researcher in the systems group at TU Darmstadt. He received his ME and PhD from IISc Bangalore. So here only. He has prior research experience at IBM Research and Huawei. His recognition includes the IBM PhD Fellowship, Huawei Future Star Award, and the Best Paper Award at the Tara Workshop 2024. His research interests include database systems, particularly database testing and benchmarking, and AI for databases. He actively contributes to the research community through roles such as proceedings co-chair for SIGMOD and reviewing for venue, including, for example, all top venue in the databases, if I can say.
Yeah.
So the stage is yours, and we are looking forward to an exciting talk.
Hello. Thanks for the introduction, and also thanks for the opportunity for presenting in this workshop. And I will be talking today about really testing and benchmarking in data systems and seeing how we can move from really static benchmarks, which is what the current landscape of testing looks like, to more strategic benchmarks. So before we do that, let's try to see which world we are in. So currently we all are using these applications, right? And these are all backed by powerhouses, which are these data systems that you see on the top, which basically govern the entire life cycle of the of data. And these are fairly complex piece of software, right? And massively large and complex. And so of course, testing these is a major challenge. And if you look at the current landscape of testing, it involves from Forbes last year. It basically tells us that about 1/3 of the total IT spending goes into testing in general, and of course a lot of a big reason for the delays in deliverables. So if you see how are we really testing these systems is by using static benchmarks. And what I mean by that is we use these publicly available benchmarks, which are like these data sets and let's say queries along with that. And the hope is that if you are doing well on these publicly available benchmarks, when you actually you also will do well there. But this is actually far from reality, because what happens is that these benchmarks really capture a part of the test space. And when you for example, let's take an example, like you have a database system and you have a client, and when you are basically let's say you have an upgraded version now, and I want to evaluate how will this upgrade really perform at my client side, right? And if you are using these publicly available benchmarks for testing, you do not really get an idea of how will it really behave at the client side, and you would basically have a gap when you look at the actual customer environment. And what this leads to is basically unforeseen issues in the client deployment. So one may ask, why not just directly use what is available at the client, right? I can just try and use the client's data directly. What problem do you see there?
Privacy.
Of course, privacy is the problem, right? So you do not have access to the client's data. So that's where we are, and we are basically resorting to these static benchmarks for testing and benchmarking. As a result, if you see the last decade or so, you have several cases where these systems have actually failed, and as a result of that, you had privacy breaches, you had monetary losses and whatnot. So let me summarize this entire setup through this example. Let's think like the testing environment and the customer environments are two different islands far apart, and you have these sharks surrounding the customer environments, which basically corresponds to the privacy and regulatory concerns that you have. And really using static benchmarks for testing is like traveling this route on a paper boat. So you are doomed to fail. And what I'm trying to propose is that we should basically, instead of using a boat to travel, you can actually create a bridge that connects the two. So by that you basically bypass these privacy concerns. So this is basically the outline of the rest of the talk. So I would start by really talking about how can we synthesize synthetic databases which can give me similar query performance as a given client deployment. And as a second part, I'll give you a quick teaser on what are the kind of challenges we see when we actually do data engineering using LLMs. So let's start with the first part. So I have, so I'll talk about query-aware data generation. So let's think about this through this toy example. I have a toy database here with two relations, register and student, and register holds the foreign key to the student table. So I have various columns listed here, and I have a simple SQL query that you can see at the bottom. Anyone would like to tell me what this query is trying to do? I hope you guys are familiar with SQL. Yeah, please.
So we are grouped by the age and then return the average score of that age.
Exactly.
We are having a filter of the between which category to which category we want. Like here we have year. So we want the data which group between 2021 and age should be greater than 25.
Right.
And then we are grouping it and then we are getting the aggregate.
Exactly. So what we are trying to do here is that for a specific year, which is 2021 here, we are for senior students, let's say, who are more than 25 years of age, we are doing an age-wise score distribution. So it's basically trying to capture a distribution. And if I execute this query, I get a query plan which is something like this that you see on the right-hand side. So what is this plan trying to say is that you have at the bottom the two relations, the student and the register. I apply the age filter on the student table, which is saying that age is greater than or equal to 25. And I apply the filter on the register table, which says year is equal to 2021. And then initially I had 50,000 rows and 370,000 rows in these two tables. And then after filtration, I get these corresponding numbers. Then I finally join these two tables and then finally apply the grouping function, which gives me 10 distinct unique age values and the corresponding scores for those. So if I basically say that I want to generate synthetic data which can give me similar query performance, let's talk about this query, right? I want to apply a filter and a join and then a project subsequently, right? So let's just focus on filter for now. What do you think is governing the complexity of filter, right? What's going to govern what's the performance of filter operation? Anyone?
The number of entries in the database.
Exactly. So it's basically governed by what you are seeing here, right? What's the input here? So if I have 50,000 rows and I'm applying a filter on top, so I'm scanning the entire table and then I'm filtering out all the rows which are greater than or equal to 25, right? Let's talk about join, for example. What would be the complexity for join?
N into M.
Yeah, so of course, I mean, there could be efficient ways of doing it, but then in principle, it's M into N, where you are saying that the complexity would be defined by what's the input these two values that you are seeing for the filtered relations, right? So what we are trying to do here is, we are trying to say that we generate synthetic data on which, when you execute the same query, or let's say set of queries if you have a workload, if I get a similar intermediate cardinalities, I'm probably going to have similar performance as well, right? Are we all on the same page? So are you following? So we call this as volumetric similarity, where we are saying that for the queries that I have, if I get similar intermediate cardinalities, no matter what the values are, right? If I match these, I'm going to get similar performance. That's the world we are in. So to do this, so this work was a part of my PhD that I did here, and we basically developed this tool which takes a query workload as input. A workload is basically a set of queries, and you take the corresponding execution plans, so you know how many rows are flowing from various operators in this query plan from an existing deployment, say. And then I want that the synthetic data also replicates the same kind of a behavior in volumetric similarity. Okay, so let's take an overview of how this tool works, right? So I have the client side and I have the vendor side. And on the client side, I have the original database, and the set of queries that they have. Right? Now I first process the schema, and then for each of the queries that I have on the client side, I execute them and get the corresponding execution plan. So now I know for these queries what's the various cardinalities like. And then this goes through a series of steps. The core of it is like is the centerpiece here, which is the LP formulation, where we basically encode these constraints that you're getting from the query plans into a linear program. And through these steps, we finally produce a database summary. This summary is basically a small table which summarizes the entire database information. Now, I use this summary on the vendor side and create like a virtual data. So this, you do not really require the complete instantiation of the database, but this summary is enough for you in a way that when you execute these same queries on the vendor side, you get similar query execution plans. And I'll give you a detail of how this goes about. So any doubts so far?
What happens to the query raised by the client side? Do those numbers remain the same, or are they also encoded?
So you get so let's say you take these you get these execution plans from the client side. So you do not know the data. You just know how many rows are there satisfying several predicates.
These numbers 25, 20, 21, they.
Yeah, these are available, but in principle you can also anonymize them, because it doesn't matter if you call an apple or an orange, right? So you can in principle do an anonymization, and if it's an ordered attribute, as long as you are doing an order preservation, it works. Yes.
But can you tell the use of that architecture for the client side? Why we are doing this?
We are doing this so that because we do not have access to the client side, right? So I am synthesizing this data now, which hopefully will mimic the same kind of query performance as the client side. So now that now let's say I changed some implementation of one of the operators in my engine, I can basically evaluate how it will perform on the client's database.
Do you also know the conditions on the vendor side?
Conditions meaning the filter conditions here. So you know these conditions, but like I said, you can also anonymize them, because it doesn't really matter if it's exactly the same value. You could map it to another domain and then use the values from that domain.
Also, the data generation, it is not exactly as the client side data.
Yeah, so it will basically adhere to these constraints. So it will ensure that you get these many rows satisfying the filter condition, but the identity of those rows will not be the same. Any other doubts? Okay. So I'll give you an example of how database summary looks like. It looks a bit complex, but we don't really need to understand the whole of it. But just to get a feeling of how it works, let's just focus on the student table that you see on the right hand side, and I basically will decode the first block for you here. So this block is saying that I have 2000 rows of a certain kind. What is this kind? This is saying that for GPA column, I have one distinct row in the range 3 to 5. I have one distinct row in the range 0 to 2. I have 3 distinct rows in the range 2 to 3. And for age and scholarship, I have this behavior where there are 12 distinct values in this range for the age column and in this range for scholarship column, and 8 distinct values in this particular nature. And I have to generate 2000 rows of this kind. Likewise, you can understand the rest of the blocks as well, right? So if let's say I have a 10x size database or a 100x size database, what would change here is basically the values that you are seeing here, but the size of the summary itself doesn't change, right? So basically you can encode a very large database through a summary kind of a structure here. Any doubts? Okay. So what it helps me with this, so if you generally look at data synthesis literature, what you are doing is typically you generate a disk resident data, which hopefully when you execute the queries on would give you similar kind of performance. But what this summary is allowing me to do is to basically generate rows in memory directly. So this summary is very small in size, doesn't really depend on the scale of the database that you are actually trying to generate. So when you actually execute queries directly using this summary, you can save a lot of effort in actually materializing the entire thing first. So what I'm really having is a dataless database over here, which really saves me a lot of time and space overheads. So this is the overall architecture of how Hydra looks like. The various green boxes that you are seeing are various algorithmic pieces that are there. I will not go into the details of these, but this is basically trying to tell you that it's a fairly complex piece, and what really goes into designing each of these is a lot of subjects that you would basically study in your undergrad, right? So these are various concepts from graph theory, linear programming, geometry, and systems in general. So you apply all of these concepts to design these, and I'll try to now give you a small example of how we handle filter conditions, and then subsequently I will just talk about various problems in general. So let's try to focus on filter constraints for now. Let's take an example with student table, right? I have two conditions over here. These are derived from the query plan that we saw, right? So the two conditions here are saying I have age between 15 to 35 and GPA between 6 to 8, and I have 7 such rows. The second constraint likewise is saying that there are the age between 20 to 40 and GPA between 5 to 9, there are 10 such rows. And what I need is that I generate a synthetic data which satisfies these constraints. How will the synthetic data look like? You can see it on the right hand side. This is a 2D visualization of the data. So you have on the x-axis the age column, on the y-axis you have GPA column. The first constraint over here that you see is represented through this red box, and the second constraint that you are seeing is represented through the green box. So you can see there are 7 points in the red box and there are 10 points in the green box. So if I generate a data which has this kind of a nature, I am basically going to satisfy these constraints. Are we following so far? Okay. So let's see how we can handle this, right? So this work was from Microsoft here that I'm going to talk about now. What they did is they basically proposed this strategy where you extend these boundaries of these constraints into the entire data space, and that way you get these 25 cells. So basically what I'm doing here is I extend this boundary through the entire axis, and likewise the y-axis. So I get in this way 25 cells, right? So how I can represent these constraints now is using these cells. So the first constraint is basically the union of the 12th and the 13th cell that you see over here. So it's C12 union C13. The second constraint is the union of C8, 9, 13, 14, 18 and 19. So the cardinality of all these cells put together should be equal to 10. Now we already see that these all cells are disjoint, right? So because these are disjoint, we can replace union with what? Summation. So you can basically replace the union over here with summation. So you can write actually as summation of C12 plus C13 for the first constraint, and likewise for the second it would be the summation of these 6 cells. Okay. So now if I basically create a variable for each of these cells that you see over here, I can represent these filter conditions using this linear program. Okay, so you have these x variables, and I need any non-negative solution which satisfies these two constraints would basically give me a database which satisfies my original constraints, right? Do you see any problem with this? Sorry? Try, you were saying something, I just couldn't hear you. Okay. Do you see any problem with this strategy?
Unknown variables are related to some unknown variables, not related.
So I think you are trying to say that the constraints are fewer and the variables are many. So that basically means that you have many solutions that may satisfy, which is okay, right? Any solution which satisfies these constraints would satisfy my original constraints, right? So I don't really care about which solution you are picking unless you are trying to optimize on certain other things and so on.
It might not be right, but I think the overall cardinality might not remain the same. Like
so I can basically sum up all the variables and equate it to the size of the original data table, right? So I can add another constraint for that.
And synthesizing data is not really required in this process. I don't need the grids that are not included in the constraints.
And what is that going to help me with?
I'm using up all of that space. I could.
So I think what you are trying to say is it's a fairly large number of variables for two constraints, so it's not going to scale well. So it's not a correctness problem, it's a performance problem. So if I create a linear program in this way with this kind of a partitioning strategy, I'm basically exploding the number of variables. So what we did differently is we had a different kind of a strategy where we say that any 2 points in the data space which are satisfied by the same set of constraints, you can basically join them and put it in a single region, right? So what you get is basically these 4 regions, where the region 1 over here are all the points in the data space which are satisfied by the red constraints but are not satisfied by the green constraint. The third region that you see here are all the points satisfied by both the constraints. And the second region here you see is all the points satisfied by green constraints and not by red constraints. You get the point, right? So basically you do not get very well-defined cells, but you get a kind of a region here which has this kind of a nature that any 2 points satisfied by same set of constraints are put in the same region. Now let's see, if I have this, what you can do is basically have just 4 variables corresponding to the 4 blocks that you are seeing over here, and have this kind of a way of encoding these for the 2 constraints. So do you see that we basically, without any accuracy loss, could reduce the number of variables from 25 to just 4, right? And this is an example with just 2 constraints. So if you have a workload with, let's say, hundreds of constraints, this really amounts to a lot of saving. And you can see that in the next slide. So we also show in our work that you basically, in this way of partitioning, you do an optimal way of partitioning, so you cannot reduce the number of variables further. So let's see this plot, right? So this basically is over 351 cardinality constraints for various tables in one of the benchmarks, and you can see that you have on the y-axis you have the number of variables, right? So it's a log scale. So you can already see you get several like 10 to the power 7 variable count saving for one of the tables over here, right? So this is a massive reduction in the number of variables you require to really encode this linear program. And if you see time wise, it's really the grid partition that you saw earlier. Actually the LP that you create through that crashed for the workload that we were using, while you could use the region partitioning strategy and solve it with less than a minute. And a simplified workload also, you could see a reduction from almost an hour to 13 seconds.
What's the difference between simplified and the original?
So it's a subset of the constraints which could be satisfied, like which could be solved by the solver. So are we all following so far? Okay, so now in the remaining of the talk, I will basically motivate some of the problems and not really go into the solutions. So let us look at projection problem now, right? So projection basically is something that you use for operations in SQL which involve grouping or distinct or union. What I mean by projection is, let's see through this example. So I have this constraint over here. The filter constraint basically says there are 7 rows within this red box. Okay? But when I apply projection, and what I mean by projection is I'm projecting it along the column GPA, I get 5 distinct values. So if basically I'm projecting these 7 rows onto the GPA column, I get 5 distinct values, right? So I can have, in addition, these kinds of constraints which would be useful for mimicking SQL operators such as group by, distinct, and union. Okay. So now, if you really look at this problem, it's far more challenging than the filters. And why is that? You could write the let's say you had multiple constraints, right? And you get this kind of a partitioning after that. Now, if I look at the red constraint, it's basically the union of R1 and R2. So I can write this constraint as projection of R1, union projection of R2. But unlike the case we saw in the filters, where these were disjoint regions, so you could just add them up. It's not just, the projections here are not just disjoint, right? So though R1 and R2 are disjoint, their projections along GPA have these kinds of values which are shared. So you cannot really just add them up. So these kinds of challenges you would see in projections, and there are several other challenges also. So I'm just trying to motivate here what kind of problems we encounter. So after all the process of how Hydra works, you get a fairly complex way of partitioning where you have regions which look something like this. So you basically say projection of all values along GPA column which are present in both R1 and R2. These kinds of encodings you would find, and that would help me basically encode these constraints into linear equations. And also talk about in the paper, we get a optimality proof, and we also give a bound on how many variables you would create through a graph theory kind of an approach. Okay. The next question I have is, how am I doing time wise? Okay. Okay, so let's step back a bit and think about, is matching row counts enough for mimicking query performance? Do you see a problem here? So far what we were trying to do is, we said that if you mimic the number of intermediate cardinalities, right? So if I ensure that I process same number of rows, I am going to get similar query performance. But do you see any gap here? From a data characteristics point of view, of course you could have things like storage layout and so on, but purely from a data characteristics point of view, do you see a problem here?
Data quality will also matter, like what type of data we are getting.
Of course, if you are trying to do some analytics on top of that, true, but here we are talking purely from a query performance benchmarking point of view. For that, it doesn't really matter, right? So like I said, if you start calling an apple an orange, it would not change the time for processing the query, right?
Null values and other constraints to challenge the adding some, like,
you can add those kinds of
noise in the data.
So those kinds of things can also be encoded in constraint side if you already are given an information from the client side about that. Okay, let me talk about it. So we talked about cardinality, but what about duplication in data, right? You could really have a lot of values which are identical. Now, does that affect things? It would affect, right? So I'm trying to give you an example over here, right? So let's take a simplified case where you have the two tables, register and student, and I'm just focusing on the key columns here. So the register has the foreign key pointing to the primary key, and I have this simple SQL query which is doing a join between the two tables on these primary key, foreign key columns. Now let's say I create two versions of this register table which has same number of rows. What differs is the values that you see in these two tables, okay? So I create these two register tables. One has the foreign key column which has all identical values, and the other one has a uniform distribution, basically covering all the values in the student table. Now the number of rows are identical, but you can see that when I execute these queries, this query on the two tables, on the two scenarios for register table, I get very different running times. And this is because the complexity of joins highly depend on the number of duplicates you are seeing. So typically if you are using, let's say, a hash join implementation, you would overflow the bucket when you are computing the hash. So it might actually spill to disk and so on also from the memory. So if you have a very high number of duplicates, it really affects the running time. So, so just mimicking the row counts is not sufficient. You should also do something like this. Okay, and another characteristics is pre-sortedness. What I'm trying to say here is, it's not sufficient to say that how many rows do I have in the column. It also matters what's the ordering of values in the table like. So if you have, for example, an order by operation that you are applying, what level of sortedness was already present in that column affects the performance when you are actually executing a large number of rows. So I have that through this example where I have taken one column from a benchmark and I created two copies of it in a single table. One copy had all the values in ascending order and the other one had it in a random order. And then I executed this query for both the columns and executed once in ascending order and once in descending order. What I see here is the running times for the same number of rows just by changing the column on which I am ordering or the sort order itself affects the running time. So again, what we see here is that the mimicking just the row counts is not sufficient. We also need to care about pre-sortedness in the data. So what we did in this work, so I'm again not going into the details, but we try to formalize how do we capture this data duplication, how do we capture this pre-sortedness in the data, and how can we then, having this information, mimic that in the synthetic data that I'm creating. So then when you execute the query on that data, you can also mimic the pre-sortedness or the data duplication in that case. So to summarize basically this piece of work, we try to handle filters, projections, joins. So I basically talked only about filters in this talk, but how do we handle projections and joins in the SQL queries? We talked about dynamic generation through the use of database summaries. We also talked about the region partitioning algorithm, replacing the grid with the region, and then a bit of what data duplication and pre-sortedness extensions would look like. What I did not cover is, so far what we saw is that you had an existing pool of queries coming from the client side, but you could in principle also have unseen queries. So can you then do something more clever to sort of also try to hopefully capture what unseen queries performance and cardinalities and so on would look like, and there you can do interesting things as well. Okay, so now that we have talked about data synthesis for query mimicking, query execution mimicking, now I will move, I'll switch gears to the second part, where basically we will look at the data engineering problem. And I'll talk about what this problem is, and then in the recent years we have been seeing that LLMs have been people are using LLMs for solving these kinds of problems, but what we saw over the last year or so that when you actually look at the enterprise level of these problems, the challenges that you encounter are fairly different, and it really gives you a very different side of picture to what the work so far was trying to look at. Okay, so this work I did with ITU Darmstadt, where I was a postdoc, and this work is in collaboration with SAP, so that's where we get the enterprise expertise from. So let's look at what data engineering is like. It's basically these kinds of various, so it's an umbrella term for various kinds of operations. You could have data cleaning, such as you could try to fill in missing values, you can try to correct spellings, you could try to correct the formats in the data and things like this. So these are all several kinds of operations that you typically do before you do any kind of analytics, right? And LLMs have been people have been trying to use LLMs for these kinds of problems, for a variety of such problems. On the right hand side, I give you a small example for entity matching problem, right? So you have two tables here, both have some product specifications. In table 1, I have a row MacBook Pro, and in the table 2, I have a row MacBook Air, and I could basically pose a problem to the LLM asking, I have this product A and this product B from these tables, are these same or different, right? And then the expectation from the model is to tell me whether they are same or not, right? So this is basically a simple example of how such problems you can encode in LLMs. And why are we first of all using LLMs? Because of course they are very intuitive in nature, right? You do not require a lot of expertise in using these, and they are ready to use out of the box, so do not really require training a lot of times. And what we saw in the last few years that they have been doing fairly well on a variety of problems. I have two problems example here, missing value imputation and error detection, and you can really see the last few rows that the LLMs are actually outperforming the state of the art already. But the picture in enterprise setting is actually quite different, which I will talk about. So you are seeing a lot of papers in this area now. But if you look at the enterprise setting, the reality is actually quite different. And what we saw here is, on the left hand side, you see sports tables, right? This is a public benchmark where you see a fairly high accuracy for, this is a column type annotation task. And when we apply enterprise data specific challenges, the accuracy already drops significantly. And then when you add more task related challenges, it further drops down. And when you have enterprise knowledge specific challenges, it really goes down in single digits. So the accuracy is fairly low when you actually talk about enterprise scale level things, right? And in our work, basically this paper is recently published in VLDB. So here we try to really characterize these challenges. What are these specific challenges? And to give you sort of a brief idea, so enterprise data specific challenges are like the size of the data, how much descriptiveness is already present, so how self-explanatory these values are, how much sparse the table is. And task-specific challenge just could be actually the task that you saw of entity matching is fairly trivial, right? You're just trying to ask whether two rows are identical or not. I mean, referring to the same entity or not. But when you look at enterprise level challenges, right, these are fairly complex. These are compound in nature, where you have to do one task on top of the other, and that way your accuracy fairly drops because the errors sort of compound. And then you have, of course, enterprise knowledge specific challenges, where the domain knowledge of the enterprise, their policies and so on, play also a role. So which are not already present in the knowledge of LLMs, right? So these challenges fairly, try to affect the accuracy of the LLMs. And what we also actually tried out is we took a public benchmark and we applied these challenges on that benchmark, and we could actually see that the performance was very close to what we saw in the enterprise data. So you could actually mimic the same kind of behavior by trying to replicate these challenges on the public benchmark as well. So in conclusion, I basically want to say that real world evaluations do not really require real data necessarily. What you need to do is to really match the real conditions. So you can pick a public benchmark, but what you really need to do is to try to get the real world conditions and apply that to those benchmarks. And that's what is strategic benchmarking, which is engineered realism. And I feel also that, a lot of there is this perception about testing in general, right? That testing is not as fashionable. Specifically in industry, people look down on this is a tester guy, he's not a developer and so on. But if you look at the world of research, right, testing has fairly interesting, a lot of interesting problems in it. And I would like to quote my advisor here actually. He has this quote which says, "Stop protesting and be pro-testing." So with that thought, I would like to conclude the talk, and I'm open to any questions.
Questions?
Any future work related to this?
Oh, fairly a lot. So, we talked about benchmarks here, right? So, typically what you are seeing so far is performance benchmarks, where we try to say that whether A system is doing better than B system on, let's say, a set of queries. But what is